Deep Adaptive Cryptographic Video Watermarking Framework, a comprehensive explanation. Introduction and problem context. The research paper presents a novel framework for protecting digital video content through an advanced watermarking system that combines traditional signal processing techniques with modern deep learning and cryptographic security. In today's digital landscape, where video content is extensively distributed through streaming platforms, social networks, and cloud services, protecting intellectual property and ensuring content authenticity has become increasingly challenging. Traditional encryption methods protect data during transmission but fail to prevent unauthorized copying or distribution after decryption. Digital watermarking offers a solution by embedding hidden ownership information directly into the media content, providing protection throughout its entire life cycle. Technical foundation and novel approach. The proposed framework builds upon three fundamental technologies: discrete cosine transform DCT, singular value decomposition SVD, and convolutional neural network CNNs. DCT converts video frames from the spatial domain to the frequency domain, allowing watermark embedding in specific frequency coefficients that balance visibility and robustness. SVD decomposes image blocks into singular values that represent energy distribution, providing stability against common signal processing operations. The CNN component introduces adaptive intelligence, predicting optimal embedding strengths based on local image characteristics rather than using fixed parameters. Core innovations. The framework introduces several key innovations that distinguish it from existing approaches. The confidence-guided adaptive embedding rule represents a significant advancement over conventional methods. Instead of applying uniform embedding strength across all image blocks, a lightweight CNN analyzes each block's spatial texture and frequency characteristics to determine appropriate embedding strength. Textured regions receive stronger embedding because they can hide watermarks more effectively, while smooth areas receive weaker embedding to preserve visual quality. The joint spatial frequency feature learning approach integrates transform domain coefficients with learned visual features, enabling the watermarking process to automatically adapt to different video characteristics. This hybrid feature learning allows simultaneous utilization of frequency domain information and CNN-based spatial representations, optimizing the modification of singular values based on frame-specific properties. Adaptive embedding mechanism. The adaptive embedding process begins by decomposing the input video into individual frames. Each frame is converted to the YCBCR color space, with watermark embedding performed exclusively on the luminance Y channel. This channel selection improves robustness while maintaining perceptual invisibility, as human visual systems are less sensitive to modifications in luminance information. Frames are divided into 8x8 blocks, each undergoing DCT transformation to convert spatial pixel values into frequency coefficients. The framework selectively targets mid-frequency coefficients for embedding, avoiding low-frequency coefficients that could cause visible distortion and high-frequency coefficients that are vulnerable to compression and noise. SVD is then applied to the selected coefficient matrices, and encrypted watermark information is embedded by modifying singular values using the CNN predicted adaptive strength. Cryptographic security layer. A sophisticated cryptographic mechanism protects watermark confidentiality. Before embedding, the watermark undergoes encryption using a dynamic key generated through hash-assisted chaotic mapping. The chaotic key generation employs logistic maps, which exhibit strong sensitivity to initial conditions, randomness, and ergodicity. The initial seed for the chaotic map is derived from frame information, watermark content, and timestamps using SHA-256 cryptographic hashing. This approach ensures frame-level key diversity, preventing key reuse and enhancing unpredictability. The cryptographic layer operates independently of the neural network, maintaining separation between security and embedding functions. This modular architecture enables cryptographic enhancement while preserving the robustness and interpretability of the watermark embedding algorithm. Neural decoder for robust reconstruction. A dedicated residual neural decoder addresses one of the most challenging aspects of watermarking, recovering information from distorted video content. When video frames undergo compression, noise addition, cropping, scaling, or geometric transformations, the extracted watermark signal becomes corrupted. The neural decoder learns to reconstruct encrypted watermark information from distorted transform domain coefficients, effectively filtering out artifacts and enhancing recovery accuracy. The decoder employs a residual learning architecture with 4 residual blocks, which improve feature propagation and prevent degradation in deep networks. Residual connections enable efficient feature reuse while maintaining low-level visual information essential for preserving imperceptibility. The network is trained using a composite loss function combining mean-squared error, structural similarity index SSIM loss, and bit error rate per loss, jointly optimizing reconstruction accuracy, perceptual quality, and watermark robustness. Experimental validation. The framework underwent extensive evaluation on 2 benchmark datasets, 11ph.org video test media and Davis densely annotated video segmentation. These datasets provide diverse content with varying spatial complexity, motion characteristics, and scene dynamics. The researchers conducted experiments under multiple attack scenarios, including JPEG compression, Gaussian noise, cropping, rotation, scaling, and frame manipulation. Performance assessment utilized several key metrics: peak signal-to-noise ratio (PSNR) and SSIM for imperceptibility, bit error rate per for robustness, and normalized correlation for reconstruction accuracy. The proposed framework achieved average PSNR exceeding 40 dB and SSIM above 0.95, indicating near lossless perceptual quality. Under attack conditions, BER remained below 5% for most scenarios, demonstrating excellent resilience. Statistical analysis and performance trade-offs. The research included rigorous statistical validation using 5-fold cross-validation and paired t-tests. Results confirmed statistically significant improvements over baseline methods, including classical DCT SVD, DWT SVD, and modern deep learning approaches like hidden and Riva GAN. P-values below 0.001 for most comparisons established strong evidence against the null hypothesis of no performance difference. The framework demonstrated effective management of the inherent trade-off between payload capacity and robustness. Increasing watermark payload from 128 to 512 bits resulted in moderate PSNR degradation while maintaining acceptable BER levels, showing the system's scalability for practical applications requiring higher information capacity. Security analysis. The cryptographic protection mechanism underwent comprehensive security evaluation. Key space analysis confirmed resistance to brute force attacks with effective key space exceeding 256. Unauthorized extraction attempts using incorrect keys produced random outputs with false positive rates below 1%, confirming strong protection against unauthorized watermark recovery. The dynamic key generation approach provides additional security against replay and known plaintext attacks. Practical implications and applications. The proposed framework offers significant practical benefits for multimedia copyright protection, content authentication, and secure video distribution. Its balanced performance across visual quality, robustness, and security makes it suitable for real-world applications including digital rights management, forensic tracking, and content verification in streaming platforms. The computational complexity analysis indicates near real-time processing capability, enabling practical deployment in modern multimedia systems. Future directions. While the current framework achieves impressive results, future research directions include developing fully blind extraction techniques that eliminate the need for reference information, improving robustness against adversarial attacks, and optimizing for real-time applications through model compression and hardware acceleration. Blockchain integration for immutable ownership records represents another promising extension for large-scale copyright management. Conclusion: the deep adaptive cryptographic video watermarking framework successfully integrates transform domain watermarking, adaptive deep learning, and cryptographic protection to address the limitations of existing approaches. By combining DCT SVD embedding with CNN-based adaptive strength prediction and residual neural reconstruction, the framework achieves an effective balance among imperceptibility, robustness, and security. The comprehensive experimental validation, statistical significance analysis, and computational efficiency assessment confirm its viability for secure multimedia authentication in contemporary digital distribution environments.